Hey, welcome back. Today I will cover a small topic on verification of signatures in smart contracts. My throat is a bit sore, so I'll not take too long on this. This is like in the roadmap, it will come somewhere in the middle, but since I was doing it for my purposes, I decided to record this beforehand. I'll change the title and the numbering later on, as and when it comes and fits in the entire roadmap. So, a signature like or any EVM related transaction, and we have seen that it is based on a private public key concept. When there is a message, the private key combines with the message, signs it, and the public key basically verifies it. That the corresponding private key signed it. And Ethers provides you with the relevant functions to be able to do this. But let's say we have a smart contract that is deployed. Smart contract on Ethereum. And we need to be able to verify signature inside the smart contract. Then how do you do that? For that we need to know a couple of things. First, who is the expected signer? Let's say that particular address straight right from public is 0x123 signer. Now we need to put this somewhere with us, like register it beforehand. So there is often something like a registry which has a list of expected signers. For a particular message, let's say 0x123 signer is the expected signer. So either you can have a separate registry contract, or you can in fact hard code it or put it inside the verifying smart contract also. So for simplicity's sake, let's put it here itself as a constant. So now you know कि any time someone sends a signed message, when you do like your magic of verification, eventually the expected value should be matching this value. This is the value to look for. Okay, so now based on this, the flow becomes pretty straightforward. You have a contract. To this contract, what are the things that you send? You send the message to be signed, and you send the signature. These two pieces of information hit this contract. What the contract does is hashes the message, extracts the digest that was signed, and then what it does is takes the digest and the signature, from this it recovers the signing address, Let's say this comes out to be 0x789 signer, and then matches the recovered address with the expected address. Since this is 0x123, while the address recovered from the signature and the message hash is 0x789, signature will be rejected. They are not matching. Only if this signing address is recovered to be 0x123, which is the same as this, will the signature be accepted. It's a pretty straightforward process. In the off-chain signing, the message was taken, its hash was derived, the hash was signed to create the signature. Similarly, here also, you take the message, create the digest of the hash, and then you have the digest, you have the signature. Using these two, basically derive who is the signer. So in a way, when this signing is happening, the flow is going like this: message to hash, and then this whole thing interacts with the private key, and this hash is again kcat 256 hash. This entire thing comes out to be the signature. This is during creation. During verification, you just invert the process. You take in the signature, you take in the message, convert it into your own hash, and then you combine these two. Using these two, what you recover is the signing address. Here also, from the private key, you could have derived the signing address. And then you have the expected signing address. You can call this extracted signing address. And then you match these two. Ideally they should be, if equal, accepted, else rejected. That is all there is to contract-based signature verification. Now let's quickly write a contract and implement this. Let's make it verify signature dot solved. We have done this so many times. First you define the Prago, defining the Solidity compiler version. Let us define the bare bones contract. In fact, let me rename it. Ideally, it should be a valid address. It's just throwing up something. I'm using this. Now the first step is receive the message and derive its Keka hash, which was signed. Let's model it similar to a transaction where the address to amount any string associated with the message and the nonce. Nonce is done to avoid replay attacks, that same signature being used across different transactions or multiple times. This will return a serialized byte 32 array of the Keka hash. First you do an ABI.encode packed so that packing or the padding zeros etc. are removed for more efficiency. And you return a Keka hash for this. Now you take this message hash and convert this into a prefixed hash which is consistent with your EIP 712. Similar to ETH_sign. This one RPC method. So we took the message hash from the above function. Return bytes array. Now we are done with these two steps. Next thing would be the verification function, which receives the message details, which is your to amount, signer, message, nonce, and the signature. The message here is this: any string associated in the original data. To return a boolean value whether the signature matched or not. First you take the message, hash it again here in the verification function. Then you convert it into EIP712 consistent prefixed message hash. And using the message hash, each signed message hash and the signature, you recover the signer. And you compare it to the expected signer that you defined above. This would be passed here. You need a function for recover signer. So you provided the message, each signed message hash, the signature. It returns the address of the signer. Then we need to finally define the split signature function. This I will write in its entirety. We'll just return the three values VRS as we saw above. VRS bytes array, and we use an 8-bit integer. Okay, so in the entire bytes array, first 32 bits stores the length of the signature, which is compared here. Then, so to access the signature itself, you need to move the pointer 32 bytes. So you move the pointer 32 bytes and load the first R value. Into the memory. Again, press another 32 bytes. And finally the first byte of the remaining 32 bytes. And that's it. We have these 5 functions: take a message, get a hash, get a prefix message and its hash, send to verify along with the expected signer, recover who is the signer, split the signature to recover the signer, finally compare the expected signer with the address who actually signed. If they match, let the logic continue, else reject and throw an error. I have really bad throat, so I'll close it here, but it was a very interesting way, and I found it initially tricky because I thought differently about this verification of the signature, but it's like you don't verify the signature itself, you extract out the address of the signer from the signature using the hash of the message that was signed, and then compare it to an existing expected signer that you knew about. Alright, thank you, see you in the next one.